Okay, hello and welcome to this first video in a series. We're going to be doing digital computer electronics. This is based on an old out-of-print book from the 70s that talks about some interesting principles and basics of computer theory, and it went from real basic understanding through to building or understanding what they called a SAP, as simple as possible computer, and from there microcontrollers and microprocessors. So yeah, that's what we're going to be doing. I'm going to be running through some things that I learned from that book and letting you guys follow along. Some people follow along better when it's presented in video form. Some people prefer to read. So for those of you who prefer to read, I'm also putting stuff up on Xperienced.tv. So if you want to follow the link, I think it's going to be somewhere down here, probably, then you can read about it. Otherwise, feel free to follow along on the videos. We're going to be doing some electronics eventually as well, but the first video today is about boring numbers. It will get better in the future. So if we think about how it was many years ago, shepherds used to count their sheep with pebbles. So they'd have a certain number of sheep and a certain number of pebbles. Let me just pull this into focus here. 1, 2. So every sheep would be one pebble. And as they went from one side of a fence to the other, they'd just pop a pebble into the next bag and transfer them over. If they had any pebbles left over in one bag, then they knew that their sheep had gone missing. If they didn't have enough pebbles, then somewhere they'd gained an extra sheep or two. It's not really easy to count, though, if you look at it. I mean, at a glance, you can't tell how many there are. You have to physically 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so 9 pebbles. That's what we call base 1, so it's not very practical. It's just 1, 1, 1, 1, 1, 1, 1, 1, 1. Just like that. The Romans kind of got it a little bit better. They still kept the 1 and 1, 1 and 1, 1, 1. But then they started to use symbols for certain numbers. So the next one would be 4, which would be 1 away from 5, and then 5, and then 5 add 1 is 6. So the Romans kind of had a better system. The only problem is 5, then 10. I think the next one was 50. Is that 50? And then 100, and then 1,000. They didn't have very many symbols for different numbers. So, for example, 1984 would be M, C, M, L, X, 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 I, V. Or MCML XXXIV. It's not the name of a George Orwell novel you want to be rolling off your tongue. But anyway, so they had it slightly better. And then along came the Hindu-Arabic numeral system, which gave everything its own symbol from 0 all the way up to 9. So everything from 1 to 9 had its own symbol. 10, well, we have 10 fingers, don't we? So this is probably where the base 10 came from. 10 would actually be reset, so you'd reset this digit back to 0 and then carry. So the next number up would be a 1, 0. Okay, so this one gets reset and you carry over a 1. Okay, that's how number systems generally tend to work. Think of it like the odometer on your car. Odometer. There's a T in there, not a D. So when you're driving along, you get a brand new car, it's all sitting at zeros, it looks lovely. You drive along, you go 9 miles, and then 10 miles comes along, it ticks over the 1 and rolls back to the 0. That's called a reset and carry. This is how we generally tend to see numbers day to day. We know how it works, and it's not much of a big deal. Let's have a look at the binary system. So this is decimal. We know this is decimal. And decimal, deci stands for 10. Okay, so it's the root of this word means 10. The next one is binary that we're going to look at. Now this is a big deal in computing. So binary, bi means 2, like bicycle means 2-wheeled. And if we take that same odometer, which is like 6 numbers, I think, and we go, so after 1 mile we get 1, after 2 miles we get that. So, and then 3 miles is this. So the reset and carry on binary, because there is only 2 digits, there's only a 0 and a 1, anything higher than a 1 has to reset and carry over. So in binary, when you write out a number like this one would be 2 to the power of 0, which would be a 1. This would be a 2 to the power of 1, which would be a 2. This would be 2 to the power of 2, which would be 4, and so on all the way up. So each number value doubles. Whereas with decimal, if we have, say, 2, 3, 32. This would be 10 to the 0, so this would be the units. 10 to the 1, so this would be the tens. 10 to the 2, this would be the hundreds. And 10 to the 3, which would be the thousands. So that's how we always remember. The columns are the units, the tens, the hundreds, the thousands. Okay, whereas in binary it's the 1s, the 2s, the 4s, the 8s, the 16s, the 32s, the 64s, and the 128s. And it goes a lot higher than that. So it's perfect for computers because electronics have two states. They have an on state and an off state, which represents binary perfectly with a 0 and a 1. So if we take a look at the way that things work, we have a single bit. Okay, so this is just a bit. We then can have 4 bits. And this is what we call a nibble. So a nibble is 4 bits. If we have 8 bits, which is what a lot of people probably know about the Commodore 64 was an 8-bit computer, that's a byte, sorry. So 8 bits is a byte. 2 bytes, so 16 bits, so this is getting into the Mega Drive territory if you ever had one of them, which is a wonderful system, or the Super Nintendo if you was more of a Nintendo kind of person. This is what we call a word. Word up. Okay, 2 words would be a D word, and then 2 D words would be a Q word, so it's a double word and a quadruple word. So we won't get into that. It's going to be too long. It's going to go off the edge of the paper. Okay, so how do we convert from binary back into decimal, so the system that we normally use? Let's take, say, 1, 0, 0, 1. Okay, so let's take this binary number here. So we know this one is worth 1, this is worth 2, this is worth 4, and this is worth 8. Excuse my handwriting, it's pretty bad. So we have a 1 in the 1s column, so we know that there's going to be a 1. Lovely. We have a 0 in the 2s column, so there's no 2. We have a 0 in the 4s column, so there's no 4. And we have an 8 in the 1s column, so we know there's going to be an 8. And all we do is just add them together. So 1001 is binary 9. How about if we do a byte? Let's do a full byte. So let's take this byte, 8 bits. So the first one we know is worth 1. Second one is worth 2, next one 4, and so on. So then looking at what we've got here, so 0 there, so there's no 1s, there's no 8s, and there's no 32. So all we have to do is add all of these together. And what happens is we end up with 214, I believe. 214? Yeah, pretty sure. So 11010110 is 214 in binary. All information in the computer is encoded into binary because that's the way electronics work. Okay, so how about translating decimal into binary? Going the other way round. Well, it's possible to do if you can remember, or you can figure out which ones to add up. So say, for example, if we wanted binary 13, we'd have to have a look. Okay, so we can't have a 16 here, so it's going to be maybe an 8 plus a 4 plus a 1. So you have to work through it like that. The other way of doing it is what we call double dabble. So let's take 2 and divide that by 13. Now 2 into 13 goes 6 times, and there's 1 remaining. Okay, 2 into 6 goes 3 times, nothing remaining. 2 into 3 goes once, remainder 1. 2 goes into 1, no times, with a remainder of 1. Okay, now I don't know if you've noticed, but if I read this from top to bottom, I get our binary number 1101. So 1101 is equal to 13 in binary. Okay, that's one way of doing it, called double dabble. It's always worth learning how to do it. And since we're going to be working a lot in binary, we're going to be focusing mostly on using nibbles of binary. So I'm going to quickly write out all of the values of a nibble and all the values of that nibble in decimal, so you can just see how they correlate. So let's go decimal here. Okay, so that's all the values from decimal 0 to 15, all the way from 00000 to 1111. We're going to come back to this later because this is actually going to be quite important. So you can see the way decimal counts up to 9, reset and carry, and then up to 15. The reason why this is interesting is when we come on to hexadecimal. So hexadecimal is the other number system that we're going to be focusing on quite a lot, and I'm going to put it onto this system here. So this is written out in a proper table on the website, Xperienced.tv. So let's have a look at how hexadecimal would count up then. So 0,
1, 2, 3, 4, 5, 6, 7, 8, 9.
A, B, C, D, E, F. Now notice hexadecimal doesn't reset and carry at any point down there. This is all a single digit. The next one would be 10. That would be equivalent to decimal 16 and binary 10000. So if you have a look here, you notice we've got one nibble, and then we've got the start of another nibble here. We've got one nibble here, and the start of another nibble here. So hexadecimal actually corresponds to each nibble, and it makes reading bytes, words and other things like that, memory locations, a lot easier, which is why hexadecimal is mostly used in computing as an easier to read format than binary. If you ever see a lot of machine code or machine language, you'll see small opcodes that they're called, and they get translated normally into hexadecimal, and then they get input into the computer system, which then translates the hexadecimal into binary. It's one way of getting closer to the actual machine's language, is using hexadecimal. And we'll be looking at this when we build the SAP as well. You'll be quite surprised at how that actually works. Converting through hexadecimal back to decimal though, let's take a look at that and see how we would go about doing this. Okay, so before we go on to the conversion, taking a look here, hexa, like hexagon, actually stands for 6. So we have 6, 10, so 16 together. So decimal is a base 10, binary is a base 2, hexadecimal is a base 16. So we have 15 different characters, we have 16 different values before it has to reset and carry. Okay, so 0 to F. Let's look at converting hexadecimal to decimal and binary. So we'll take the hexadecimal C, 5, E, 2. Okay, like so. So converting this from hex to binary is really simple, because you just do it nibble by nibble. 2 is 0010, E is 1110, 5 is 0101, and C is 1100. Okay, so you can use that chart before to calculate what the binary is. So that would be the binary equivalent of C5E2. Okay, so it's 2 bytes, so this is a word. Okay, converting hexadecimal into decimal, you'll have to go through binary first, then convert the binary through to decimal. Now, this is going to get a bit crazy. For example, this digit here is 32,768. So you're going to have to add up all of these, and it's just crazy. C5E2 is actually equal to 50,658. Just so you know, you can actually check that on a calculator, because I did. So you have to do all of that, and it's just crazy. It's easier just to work in hex and binary without converting it back to decimal. There is a system called octal, which I'm not going to go into here, that's used mainly in old mainframe computers and Linux permissions. But we're focusing mostly on hexadecimal and binary. You can actually convert decimal into hexadecimal using the same technique as before. So for example, let's do 17, because it's easier because you have to divide by 16. And so 17 in hexadecimal would be 1, remainder 1. And then 16 into 1 doesn't go, so remains 1. So hexadecimal 17 is actually 11. You have to really know your 16 times table to be able to do that. It's called a hex dabble, and it's just a nightmare. Converting hexadecimal into decimal, there's no real easy way to do it. I suggest you get a computer rather than doing it through your head. There is one other system as well that I should mention, apart from the octal, and that's binary coded decimal, BCD. A lot of real-time clocks use binary coded decimal. I think the NES also had a binary coded decimal register. What that basically means is you take a decimal number, say 2945, and you convert that into nibbles. So this would be the decimal, and the binary coded decimal will be 0010, 9 is 1001, 4 is 0100, and 5 is 0101. So that would be the binary coded decimal for 2945. Okay, binary coded decimal is useful. It's a lot easier to convert back to decimal than regular binary. It's slightly inefficient though, because decimal, the highest number is 9. So that means you're missing out on 6 values in the nibble. So it's an awful waste of space, pretty much. Okay, so that's all for this video. I tried not to make it too long, although I think I have gone a little bit over of what I wanted. I wanted to try and get it down to less than 15 minutes, because it's a boring subject, really. Next time we are going to be looking at logic gates, so there will be a little bit of electronics, and we'll be looking at transistors. In the meantime, if there's something that's not clear, please drop a comment, or if there's a question, and I will try my best to answer as clearly as I can. I do try to read as many comments as possible. At the moment, while the channel's still young, I can read every comment, which is marvellous, and I can get back to you all individually. Please check out Xperienced.tv, where I'll put the text version of this up on there, so you can read it if you fancy. And that's all. So until the next time, until the next video, thank you very much for watching. Please leave feedback about this series, and yeah, catch you later. Bye bye.